to this webinar on regenerative residential design, another exciting topic for the day. My name is Marloes Reining and I'll be your facilitator today. Okay, so very exciting. We have a sponsor for this webinar, and that is Solar Solutions and Technologies. They are specialists in the installation of complete solar systems for businesses, farms and private households, so that they have full capacity electricity at all times. We are switching businesses, farming and households to go green. So I'm just going to show you a short video about the company and what they are all about. Great, thanks.
I want to tell you a little bit more about what we are trying to do in Cape Town with regards to energy, particularly to end the scourge of blackouts in our city. Now, load shedding and rolling blackouts are the #1 handbrake on the South African economy.
Since I've purchased the electric motor, I've saved. My petrol cost used to be 5,500 Rand, and with a decent system installed on solar, it's actually costing me 0 Rand per month. Now to charge your car, do the following: open up the flap on this side. Now you're charging free energy from the sun. Right, load shedding has disrupted a lot of people's lives. However, it's also created a massive opportunity for solar systems to become totally independent, even to reap the benefits of grid feeding and to be financially rewarded. And so they've actually done you a favor. You've realized the fact what solar panels can do for you, and you can save tons of money. The system can be financed over a period up to 10 years, and from day one, your cost of finance versus independent renewable energy just makes sense for you in the long run, and you've got your own system. Alright, so I've installed 8 5.1 100 amp Revolve batteries, deep cell lithium batteries, which are the best. There's a 10-year guarantee on the batteries with an extended warranty of additional 5 years if you wish to choose. You can get up to 6 cycles on the batteries. These batteries are being charged from the SunSync inverter, which is a 16 kV SunSync inverter. And what it does is your PV panels are being fed. It comes in here, as you see over here, and the machine then converts this over into electricity, and the batteries is converted from there. The batteries then feeds into the house. So this house used to spend in excess of 7,000 Rand a month on electricity. Currently, electricity spent at the moment is 0 Rand. So on the actual inverter, you'll notice I'm using 11 kV because the car is charging at the moment. So free electricity for the house and free driving experience because of no fuel, no cost to your fuel bill. I find myself in a very different mindset where I had to adapt, especially after I took this house as a showcase, and I wanted to prove to myself that solar can be the answer to a total dream. This house had a fixed cost of 22,500 Rand, which included fuel, it included water, it included cost of electricity. I've wiped that out to rates and taxes at this stage, which is 3,000 Rand. So from 22,000 Rand, I've gone down to a total saving of 19,000 Rand. Today, I've generated 64 kilowatts of energy from the grid that you noticed behind me. Right, so Nano has supplied me with the clear fence. Nano is the best, and the product comes with a 10-year warranty. I've also, the 5 main lines at the top has been connected with 7,000 volts should somebody try and break into your property.
I see Johan Muller just joined the webinar as well. If you guys have any questions on the solar systems in the video or where to get his contact details, we'll also share the details of the sponsor in the chat just now. So yeah, just pop some questions out to the sponsor if you have one, if you have some, and thank you again for sponsoring the webinar. Just a note that all our previous webinars are uploaded on the GreenNet website. So if you have missed one, you can go back and have a look at them. And if you're looking for some place to volunteer your time, we are always looking for help and on admin, on organization. So if you have a couple of hours free in your spare, reach out to us. We can.
So firstly, thank you, Luce and the Regenerative Collaborative of South Africa for arranging this webinar, and to the audience for being here with your attention and time. Right, so the goal today is to present a logical and concise overview of building performance modeling and to bring this work to life with some examples from recent projects at Ecolution and Climatric. So to start off with, building performance modeling is a process where scientific computer simulations are used to test and learn about the expected operational performance of a building and its climate. So we test and learn and improve performance before we build. And it goes on the concept of what we measure we can learn to manage and improve on. So yeah, and in addition, there's also the process of finding a balance between competing objectives. So we're using computer simulations for this. The brains of many building performance computer simulations would be Energy Plus, which is an open source whole building energy simulation engine from the USA. It's already been in use for 25 years. And yeah, this is regarded as the best in the world, adopted by many interfaces. Now, an interface program helps with adding data to this program and getting it out in an easy way. So yeah, I have been using Design Builder software for the last 10 years or so. It is a user-friendly interface for Energy Plus since the year 2000. It's been supported in South Africa for 10 years and is accredited for SANS 10400 XA work. And everything is seamlessly contained in one program that works. So I definitely highly recommend it. And I know Dolf uses Rhino and Grasshopper. Perhaps he will tell you more about that during his presentation. So now that we have a simulation program to run our models, we need to look at how to set up a model. And it's for me, it starts with the climate. If you do not understand the climate, it's good to review the climate data and then load it into the software. And this climate data would be hourly data and everything that the model would require to determine energy flows in buildings, from temperature, humidity, wind, you name it. Right, then following on from that, one would set up the 3D geometry of the building and assign constructions. So the thermal mass and insulation, glazing and shading. And at that point, the envelope of the model would be defined. The next step is to look at what people are doing or would be doing in this building and the times that they would be doing that, and also what equipment they would be using. Because everything inside a building, or most things inside a building, would give off heat, and this needs to be taken into consideration in the model. Yeah, and then one would also need to set up what type of HVAC or heating and cooling system is in the building. Yeah, so now we've defined or added all these details to the model. Now it's time to run simulations. And of course, before doing that, one would simply just do some test runs to make sure the settings are operating correctly. So with the results, we want to look at the performance. And I like to summarize the performance as something related to the flow of energy in the building. So here are some examples from my work that I can name. I'm sure there are more. So, for example, energy demand and consumption, natural ventilation and lighting, detailed testing of HVAC systems, renewable energy systems, and then also thermal comfort, airflow, and glare. Right, so building performance modeling, for me, it slots into sustainable energy design. And this picture is a good summary for me. It represents the energy use of a building over its lifetime. All right, so, and if we're applying building performance modeling to the bottom two tiers, we can test and improve and effectively shrink this footprint. And the result is that your mechanical and electrical equipment in tier 3 would, number one, be smaller and also consume less electricity, less frequent use. So that is the aim. Okay, just a bit of context also. Broadly speaking, I would divide building performance modeling into two categories: design and operational modeling. So what this presentation is about is mostly design modeling, where we test and learn and improve designs or select the most appropriate ones. The other side is where we go one step further or use a fixed recipe to test and score a building. And examples, and this is very important in our industry, plays a big role. So this would be Sunstein 400 XA and Green Star SA modeling as examples. I think that is basically the overview from my side, just as an introduction to building performance modeling. I'll hand over to Dolf.
So I'm going to now take where Thomas left. So he gave a brief introduction, and I'm going to show examples of building performance modeling and how we can take that further. So as Thomas has told us, we may create a 3D model, a digital twin of a building that we can use for simulations. And so this would be a typical building, and this could be, for example, your model that you create for your Sense6A qualifications. So what we can do now is take this model, and we can actually get a whole lot more energy, a whole lot more information out of it, other than just the Sense6A performance. For example, this is the same building, and here we look at the solar performance of the site and the building, both on ground level at a 3-meter height level, which allows us to map what's the best location to put your solar PV panels. And then we can test the performance of those PV panels and how that relates. So what different scenarios can we think of, and how does that impact then your energy costs over the period of the lives of 15 years or something. These analysis, then we can get into a whole lot more detail. So if we're in a mountainous area, we can take the mountainous area into account. And then same thing, like in this example, we're actually not mapping for solar panels, but we're mapping for landscaping. So these are different seasons, solar performance over the different seasons. And based on that, it's a luxury thing. It's not every project, but planting schedules were made based on this. But the solar performance is then mainly we use it for building design, and it's a very simple 3 classrooms under a tent design, where you can see then how we use a graphical representation of data to allow it to use it in workshops so that we can adjust and update the building design on it. But other than solar data, there's also a lot of other information that can come out of the same model. So here we are looking at daylight modeling, where we have 2 different scenarios of window ratios and how that impacts the daylight design and if it's still compliant to the healthy lighting building code. Or wind analysis. So wind from a whole lot of directions. We use typically 8 directions to use a wind analysis, and that we can then use in early stage to identify problem areas. So where's your wind coming from, and how does that impact your comfort? So these first examples were smaller scale, but it speaks for itself. This also translates to a lot bigger scale buildings. In this building, big apartment complex, we're specifically interested in the PV performance on the facade. So they wanted to put PV on the facade, and where would the best location for that be? And what we also did with this one is that we then created a wind analysis, but not for just one direction, but as I said, for 8 directions. And those 8 directions then allow us to make a wind map for every hour of a year based off climate data. So then we can see how strong is the wind on the grid of your site. And if we have that wind data for every hour of the year, then we can start combining it and create outdoor comfort analysis. So then we can combine the wind with humidity and clothing and activity, etc. So we add the solar radiation data again to that. That allows us then to do outdoor comfort analysis and map the results for different time steps, whether it's cold or warm. It creates these beautiful zombie maps, which give us an indication of what the comfort is. So it's more a workshop tool that we then use. So typically in the Netherlands, this would be used, for example, for where do you put your outdoor cafes, where do you put your bicycle parking? Kind of you can optimize your real estate value using this and prevent dangerous corners with very high wind velocities occur. So what we do outside, we can then also do on the inside. So on the outside, you get a lot of vegetation that keeps you comfortable, but on the inside, all your building surfaces can become very warm. And so, for example, what we had a glass building, they were thinking of using tinted glazing to make it more comfortable because, the tint blocks the sun, so it should be colder and more comfortable. But we can also calculate these values down. What will the window temperatures be? And actually, darker windows become hotter, and net over net, you're in the same comfort result. So, micro lesson to take away from this is that if you replace your windows with tinted glazing, you do not make it more comfortable. And so, again, those things we can then map, and we can create different scenarios. We can test it and see how we can make the space that's a very difficult space to make comfortable, turn that into a comfortable space. And that's then, you can see here, is the result at Hazendal, where we have the glass house, which is very comfortable. And then one other thing that we do, and so if there's one thing you take away from this presentation, it's this part, so pay attention. It's the parametric analysis. So that's where we take that 3D model with the thermal analysis you can use for Sense6A, but we repeat it for alternative scenarios. But if you, for example, use 2 types of glazing, like double glazing, single glazing, and 3 types of insulation, you already got 6 different models you have to look at and study. And if you do that for an overview of scenarios, as you see here, this is already 17 million designs that we would then analyze and test. So that's what we do. Well, not 17 million. We do use a bit of our own intelligence before we start, but we take many, let's say, tens of thousands of those designs, and we create all the variations. From each design, we get hourly results, like temperatures for each room, heating capacities, cooling capacities. And all of these values we can tie back into one graph, which then actually becomes a design tool for the client and architect. And it's also a motivation for your investments. So this is this graph, and I'll show it, for example, for a little car museum. We used a lot in residentials, but it's just easy to show the example using this museum. What you can see in this graph, instead of a normal x-axis and y-axis, we got a lot of axes parallel to each other. And we got input axis and output. And output can be comfort performance. Is the space comfortable? Is it meeting spec? And financial performance. How much does it cost? And we can also use then total cost of ownership calculations, let's say for 15 years. And just to explain a little more, so for example, this is roof insulation. You can see there's 0 centimeters, 6 centimeters, 12 centimeters, or 20 centimeters of roof insulation are the variations to be analyzed. And these are then, for example, maximum temperatures that then vary from, let's say, 26 to 40 degrees. And then I'll jump to this graph quickly. So this is the graph then shown. And in this building, we started originally with actually nothing happening in the building. So we had a bit of insulation, clear glazing. And what you can see is then the maximum operative temperature is too hot. The days above 30, which was the threshold in comfort requirements, was the highest possible. And the investment was low, but it was not a compliant building yet. So what happened with this building, that we had a workshop. We spoke through what we could do. So we could consider earth tubes, and we could consider floor cooling. What you can see is that you can use earth tubes and floor cooling, but you can see that the maximum operative temperature is still above the 32 degrees, and it's about 22 degrees above 30. So it's not compliant. So it's 22 days. So 22 days, you can kind of negate that, but that would be the full peak season of this museum. So during the peak season, you can't use the building. But on the other side, now we do have a more realistic investment scenario. So what we can now do is start with the costs and filter away back the other way around. So what you can see here is that when we filter back, you can see all these designs are then cheaper or the same cost as what they intended to invest. And now we can also filter for performance, and we can make it that it's all compliant. And what you can see is that there are now 20 designs that are compliant. And what you could do, for example, which would be an engineering thing to do, you can filter it back, and then you can see the most cost-effective scenario uses dark tinted glazing, earth tubes, and shading. But what also happens is we use this in a workshop. So as soon as we started filtering back, the client actually noticed that he can use clear glazing, which was in his mind never an option before, because they thought they needed a tint for the comfort. But we could show then that the clear glazing actually also performed good, but the only thing that they now had to do is they had to also install more roof insulation. So in this case, you change the parameter, everything changes. So this is now the new optimum. And you have the roof insulation, again, the earth tubes and the overhang. Now I have to switch back. So yeah, and this is then what was installed. So the earth tubes were installed on site. So this is then free air conditioning. The air cools down, the earth cools down the air that's blown into it. And that's then blown into the space. And this is the space on the inside. And as you can see, you don't see a lot of installations because there's only along the side there are floor grills, which then blow in the air in a displacement ventilation method. And when you look at it from the outside, you can see the overhang. And the overhang was not in the original design, but after the workshop, this was then added. So that's just a brief overview of what we can do with all of these models. And next, I have an example of a residential building and the kind of a design process we go through. We quickly sneak peek in the chat. I noticed there's a question was what make of BIM was used to create the digital twin. So Thomas mentioned he typically uses Design Builder. We also use Design Builder very often. The examples you've seen here, we use Rhino 3D with Grasshopper, and then we use the Ladybug tools. Okay, then I'll jump into the next example. So it's a building designed by Sky Studios in Madrid, and then Gas Architects, the team from Cape Town. I'll just go through the process, and you'll see how the different elements, different design analysis we do feed into the process. So we started with a concept design. We got a concept design from the architect, and like concept sketches, site plans where you can see there's a elevation happening over the site. And what we typically do is also what Thomas mentioned. The first step is climate analysis. So what is the local climate like? What are we dealing with? And this was towards Hout Bay. So, but Hout Bay, Kommetjie, Cape Town. Well, everyone in Cape Town knows, but so it's much colder on that side. So your design is then impacted because of that, because you always have to design for your climate. So, yeah, well, with that in mind, we helped the architect, made a first model, the 3D model of this is in Design Builder. And in the 3D model, we include the local context. So in previously you've seen like the very fancy mountains. There's also a simple version which we do, which performs equally well and saves a lot of calculation time. And based on this analysis, we can do like a first hit, just passive analysis. How does the building perform if we don't do anything? And it's not very surprising, but it gets very cold. So you definitely need heating, but it also gets very warm. So you also need cooling. Just explaining this graph actually a bit more. So it's for every month of the year. For all the spaces, it's then indicated how many days. Is it too hot or is it too cold? Yeah, but it's like it's a comfort map of the building. And then based on the comfort map and climate data, we can then suggest, okay, you need cooling, you need heating. You could consider using tabs, the activated floor, so that you can have both heating and cooling. Your cooling is limited, but it works well. The benefit of that is that you can use, if you use a system like this, you can connect it to different systems, like you can connect your floor to a fireplace, you can connect it to a water source or a ground cooling source, you can connect it to heat pumps, things like that. Other things that we're considering is, well, of course, insulation and earth tubes and alternative systems of heating. So that's where we started. Well, just like we did the blue lines for the car pavilion, we then did it for this building, for different roof setups, floor setups, wall setups, glazing, shading designs, with and without the structural cooling, and different earth tubes designs. So that's about 7,200 systems that we then look at. And for example, this is then when you zoom in, the different shading designs. So we create one basic shading layer and then we analyze it for different levels of extension. And then we can see how long should the shading be. And yeah, not to show the whole movement again, it's a bit more complex when you start looking at residentials because you have a lot of rooms and a lot more input, a lot more data. So that's why I'm just going to show the results now. But so we did the blue line graph, and for example, you can see a clear difference in performance between single low E and double low E glazing, where the double low E is a lot more comfortable. And so from that analysis, the output was actually, well, optimize insulation all around. We're going to use earth tubes, the structure heating cooling, shading, and ceiling fans. And ceiling fans is another important detail. So again, if you want to remember one lesson from this workshop, this is another lesson you want to remember, that ceiling fans are actually very important in your South African design. But we actually didn't want to go for ceiling fans in this design, so we're trying to replace the ceiling fans with earth tubes. So very quickly, why are ceiling fans important? Well, if you take a comfort calculator where you can have human activity, clothing, conditions, which you always have to do for a local climate again, you can calculate what are the temperatures above which you start getting it, after which it becomes too hot. And so if a normal office environment, you might be designing for like 25, 24 degrees. If you're inside, your clothing is more relaxed, you can go up to like, say, 29 degrees. And above that, it's getting too hot. But if you now switch on a ceiling fan, in this case, this scenario, because it's less humid, you can actually go up to 33 degrees. So that means that if you have a ceiling fan or another type of air movement, another ventilator, you only have to switch on your air conditioning once you hit 33 degrees. So you reduce the amount of time that you need your cooling system significantly, and you save a lot of energy by doing that. Well, then the earth tubes. So the earth tubes, we could see in our results when we zoom in, we get data for every hour of the year. So temperature, performance, you see the outside temperature peaks at this day. And you can then see that the design with earth tube, without earth tube, and with earth tube, you can see that the design with earth tube performs a lot better. Yeah. And for example, same thing, you can see that the design without earth tube goes up to 30 degrees. So that's above the threshold of 29 degrees. But with earth tube, you're actually still below it. So it's 27. So it does make the space more comfortable. The important lesson is also you have to really consider it for different spaces because it's not a silver bullet. So for this space, for example, the earth tube pushes us up to 31 degrees, and then it becomes questionable if the earth tube is worth the investment. Well, and since we're in a regenerative network and we want to make better buildings, another thing we were considering, but it didn't go ahead for this project, was to use compost heating. So compost in the core can become very warm. It can go up to 70 degrees. So you can't get that temperature out, but you can still use the temperature for, let's say, underfloor heating. So you can use it as a stable heat source for your building. It is a massive pile of compost, so it's like 4 to 6 meter diameter. We came to this design, but it is something interesting you could consider for your projects as a heating source. Yeah, so other than the thermal analysis in the early stage, we also did outdoor analysis. So we did more detailed local site analysis. The Lidl's line head is shown there, with again the solar and the wind in there, and that we combined that in outdoor comfort analysis. So we mapped around, looked at different times on the site, and when is it comfortable, and are the spaces where we wanted people to sit, are those comfortable at the times of the year that we want it to be. And in this case, we didn't have our little zombie army yet to map the entire site, so we were moving around the little man. And again, one little man lesson in this, so the conclusion is not very surprising, but the little man wanted to sit out of the wind in out of the direct sunlight in summer, and not in the wind and indirect sunlight in winter, which is like not a massive surprise, but it is very climate dependent. So this is really differs per climate zone, and so that's kind of why it's interesting to look at. Okay, so then basic design is made and the project evolves. Actually, more information becomes available. We now had more tree information, so we could update our models using that. And there was a bit of optimization we wanted to do, considering earth tubes, ceiling fans, and glazing. So the earth tubes we had in, and everyone was happy about it, and they were replacing ceiling fans. But still, those things, although it's a effective way of cooling, it does cost money to install. And we wanted to actually see, can we get away without earth tubes? And what we could see for different spaces is that the earth tube threshold, without earth tubes, we were kind of still in the ceiling fan comfort range. Well, we looked at the different spaces, and multiple spaces indicated that you can actually get away then without the earth tubes, but then you need the ceiling fan. So budget-wise, we were then flipping back to, okay, maybe we do want to have ceiling fans instead of earth tubes. But the other thing that happened is that we were considering, we wanted real clear glazing. So, you know, the double low E glazing, it's a clear glazing, but once samples came in, it was actually decided that we actually want clearer than this. We want a very clear view. So that's a higher priority. And again, when we have one of these comfort maps, if we had the double low E glazing, you can see you get above the temperature thresholds, but it's manageable with earth tube and ceiling fans. And what you can then see, if you change the glazing to low E glaze, single low E, it improves a bit, and while the temperatures increase a bit, so you have to start being mindful of that. But when you go to clear double glazing, the temperatures increase significantly. Because now less solar is kept out, a lot more heat is coming in, and now actually both earth tubes and ceiling fans are again needed to make it comfortable. So what happens then? Well, the design moved on and the design evolved, and what actually happened in here is that the building got redesigned. The space was 8 meters wide, it became 6 meters wide. The space became less high, so the overhang had a bigger impact on the building. So the building actually was redesigned so that it was now possible to use single clear glazing. Now, so it was fixed by passive design performance, which might have had other causes, but at least it worked for thermal comfort. That was one of the things. So the design was again evolved to make this clear glazing possible. Another thing that happened, one of those small lessons you can take out of this, is that we had a gallery space oriented towards the south. So for the Dutch people, that's in this case the what would be the northern hemisphere. So it's this is the not sun-oriented side. It was a glazed gallery space, and then we had the bedrooms, and it was moved to the other side. But what happens when you do that is now suddenly this space is sun hit, but it's very narrow. So it's compared to the, let's say, the entire volume of the space, there's a lot of sun happening here. And it becomes extremely hot in these spaces. It does help for the rooms. The rooms are set back, they're more sheltered, so that's comfortable, but the corridor becomes too hot. But also, this was then worked through, workshopped, and discussed. And actually, what you can see, all these elements are openable. So what the solution was in this case is that all these spaces that were still like trouble spaces, they became fully open spaces. So in winter, it would be closed. It would be an internal space. But in summer, it would be open. And then suddenly, this is a space with a nice overhang. And it makes it, yeah, design. So design updated, again, tested the comfort map, and well, yeah, it all worked out. So the double glazing was made possible. The earth tubes were out, but the ceiling fans were in. And actually, for uniformity, ceiling fans were then added to all spaces. And the difficult outdoor spaces, indoor spaces, actually became outdoor spaces when it was too hot. It was an indoor-outdoor scenario to deal with that. Other thing that we focused on was the shading design. So the shading design, because there was a glass, has had a big impact. We did a lot of analysis on it already in the early stage, which gave lengths and dimensions. It was also considered the earlier stages. Can we actually do only with vertical fins? This is one of those other lessons. On the north facade, Dutch for the south facade, actually your horizontal shading does so much more than your vertical elements, and that's also something you can see in the results, that you need the horizontal shading. And I think this, yeah, because the temperatures are much lower. But what we then did, and this was a bit of a over design and more a geek out. Dolf had a fun weekend. We looked into a lot more detail in the shading elements. First, we used our thermal model, the results that we already had, and combined that with optimization on what kind of lengths do we need, what are the optimum lengths for our shading analysis. And then we went parametric again, and we started designing many different iterations to come to optimum material spend. So how can you, if you want to spend less money, so you want to buy less timber slats, how can you get to optimum design? But it's again combined with aesthetic design, and this is then actually the result that came from that. But again, so it's not, this would not typically be an analysis that we do every time, but you can get the lessons from it. So if you do the analysis, so if you want to learn from this and just take the results, a more denser design works very well. But if you then want to scale down, first remove the perpendicular slats, they do less, so keep more of those. If you then want to reduce even more, move the slats around so that they're more close to the window and less far away. And if you want to cheat, then you just rotate the slats. But so if you want to cost optimize design, you kind of come down to this. Yeah, so after that, wind analysis won't go into a lot of detail, but updated the design as well. And to improve comfort, it's like, please add some walls here, here, and here. You know, there's a wind tunnel here. We want to block that. But the other interesting part was the wind is redirected here and creating a tunnel effect here. So actually, can you open this fence? It was a fence, was created a wall, but can we make it that it lets through the wind so that the comfort will be better? And solar, so also again updated solar analysis, but in this case we used it for a PV analysis, and we do our PV analysis where we check the balance of how much is it using, how much can we store in the batteries, and what are different loads doing at the hours at the time. So this is actually, we look at the performance of the building for every hour of the year, so that we can figure out how much is going into the battery, how much is being used, how much are we charging. And the lesson from that, so again, if you don't want to do all the analysis, but you just want to take away the lesson, is that actually, if you want to go fully off the grid, your passive design is very important. So this is heating, cooling, and domestic hot water. Domestic hot water you can tackle at maybe the compost heating or at hot water elements behind your PV panels, like PVT panels. But your heating and cooling is a big element. So that's, if you want to have a passive building, then you really need to focus on that. I actually realized that this is not a graph from the Pacific project, because we had a good passive design, but we had a professional kitchen, which actually threw off the balance in this case. And the other thing that's then learned, like this would be actually typically a starting point is, this is how much energy is produced, but this is only how much is used and how much is taken from the battery. And this is how much energy we're actually still drawing from Eskom. And so you want to be optimizing your battery capacities. And you don't want to go to 100% battery capacity because that's very expensive. So again, if you don't want to do all the calculations, first hit numbers, you want to go up to kind of 80% of your capacity for your system. And that's it. So that's then the results. And this, well, construction is happening at the moment, but you can see outdoor settings were created so people can sit in the shade or in the sun. They can here move closer to the building and farther away. The shading is implemented, so it's both beneficial for sitting outside and for the room temperatures. On the inside, you can see tiles are used combined with underfloor heating, cooling. So it's thermal mass that absorbs energy. It also allows for windows to be opened, and that's what you can see. So the windows openable on both sides, so you can get a cross breeze for extra comfort. Yeah, so and the cross breeze happens to all spaces. That's it in a nutshell fly through. I hope I take up all your time, but that's it for now. I think it's back to Thomas.
Thanks, Dolf. That was a lot of information in a short period of time. I'm sure people are a bit blown away, but keep the questions going, and I'm sure that Dolf can answer some of them while Thomas is presenting. So Thomas, I'll give you a little extra time if that's what you want. Go for it.
Thank you very much. Yeah, Dolf, thanks for that. You showed a lot of examples of passive design in action. That was really impressive. Yeah, really interesting. Thank you. Yeah, I'm going to try and cut it a bit shorter, but yeah, so I'll dive in, and please bear with me. Sometimes I'll go a bit faster across some of the slides. So a few notes to start off with. All right, so as you've seen, Dolf showed a lot of pictures to tell the story of the modeling that is done. And so we use data and we look at it in many different ways, sometimes from close up and sometimes from far away, or averaged to see a trend. Yeah, so we jump between different ways of looking at data. And then the other thing is there's no perfect model of a real building. Models need to be as accurate as they need to answer the question that they're required for. And if your name is George Box, you might even have this quote: all models are wrong, but some are useful. All right, so it's good to keep in mind. All right, so yeah, as I've mentioned before, starting with the climate is something that I always do, especially if I don't know the climate well. If it's an unknown climate, it's worth spending some time getting to know it, looking at the data in different ways and making sure you get the most representative data. All right, so most energy modeling data would be, or the most accurate energy modeling data would be from known locations such as airports in countries that have historical data over many years. If your location is not near an airport, you might use software like Meteornorm that would interpolate between known locations to find the most representative data for your site. So once you have that data, you can analyze it with software, free software like Climate Consultant. I'm not going to go into that today because we have a lot to cover, but that's very interesting. It's a very interesting topic indeed, and opens up climate responsive design. So what interventions work well at this climate? That's even before testing it in models. So just from the climate data. So here I just have an example of, so instead of looking at 8,760 hours of data for a year, we're looking at average data, just to get a high level overview of an average hour for an average day in each month. And so that, and then coloring it just to see, okay, where are the hottest months, hottest times, which areas should we be looking out for? All right. I think it's important that designers are all aware of ASHRAE Standard 55 for low energy buildings and net zero buildings. So basically, in simple terms, this standard says that in naturally ventilated buildings, humans can adapt with the seasons, and we are comfortable over a larger range. So in the winter, we would have 90% comfort between 19 and 24, and in the summer between 22 and 27. I think this data is for Cape Town. All right, where a conventional air conditioning system might condition between 20 and 24 all year round. So so this is, and this can be further improved on, as Dolf explained, with ceiling fans. So this is a great energy saver on on projects. All right, so once we have our geometry of our building, it's really important to keep track of exactly where the sun is with respect to the facades, and studying the building helps us to choose clever designs that can improve it. So this would normally be a big part, like at the start, just to make sure we're testing sensible variations on the design. So once a model has been set up, and I like to summarize it in this format so that everybody's on the same page in terms of what variables are going to be tested. This scenario was, this residence was to be built in Durban, and at a southern elevation, which is great. And in this case, we wanted to test roof insulation, different glazing types, and some wall types with various amounts of insulation and thermal mass. So often, in my experience, the most problematic facades are on the Western orientation, and this image just shows it, highlights it again. 4 hours in the afternoon, once the building has already had the whole day to heat up in the summer, causes big problems, normally resulting in very large air conditioning systems in those spaces, or the requirement of some sort of external shading. So most places in South Africa are, in my experience, cooling dominated during waking hours. So that's an important point, because in modeling, we have to balance different things. But often the designs end up being cooling dominated because of the hours when we're concerned with thermal comfort. All right, so with a cooling dominated climate, solar design is basically the most important area to focus on in my experience. All right, and glaze would be a way to reduce overheating, but normally it's a fixed variable, or often it's close to fixed in residential designs, because we want to optimize the views, right? Right, and then the next step would be external shading. On north, that would be overhangs, and in east and west, that would be vertical shadings would be the most effective. And then after that, glazing type or high reflectivity blinds. Blinds on the inside, just remember that the heat would already be captured inside the building. So although you would block out direct sunlight from falling on occupants, the heat will still be trapped inside the building if it's not ventilated out. Right, I wanted to make a brief remark just on the portion of sunlight. So this graph shows the sunlight on the surface of the Earth, and roughly half of it is visible. The other half is heat. So typically good for the South African climate is to have low solar heat gain and a high visual light transmittance. Okay, so that we can get the highest daylight levels, but eliminate the heat. So, okay, yeah, Dolf touched on this. Yeah, tinted glass often has high, a lower solar heat gain coefficient, like, for example, this one here. And it also lowers visual light transmittance. So it actually absorbs the heat of the sun, making that glass pane hotter. But overall, it reduces the energy flowing into the building, but it can have a negative effect on thermal comfort if you do not install it inside a double glazed unit. But overall, an important takeaway here is the important property to look at in terms of reducing summer overheating is the solar heat gain coefficient of glass. All right. I find it's important in reports to just summarize model settings. So yeah, because that allows projects to be reproducible, and so that one can look at the results in context of what were put into the model, right? So I'm not going to run through this in detail, but yeah, just showed you an example of what that would look like. Also, another initial test that's quite common in my work, I try to keep the data small here, not too many rows. This would be peak demand cooling, or demand simulations that uses ASHRAE sizing methods. Yeah, for a hot summer day, and it's used to size air conditioning systems. And so, yeah, basically in this example, we tested with or without vertical shading, and one can see firstly, which zones are problematic, which have the highest loads, and which interventions work in which areas of this building. But this is just the starting point. So it's just a single day simulation, worst case scenario. The next step is to apply many of the interventions that work the best in an annual simulation. So the results shown here is it's only half the year, and it shows an annual hourly simulation with a mixed mode operation. So that means that natural ventilation is allowed when favorable, but the design builder program will automatically switch to air conditioning when natural ventilation is not favorable, according to certain inputs. And yeah, this can, yeah, in some projects, this resulted in, up to 80% reduction in air conditioning electricity consumption in the Cape climate. So that would be very climate dependent, and also, yeah, dependent on how well natural ventilation can be controlled. Right. Now, it's important to zoom into like small areas of this data sometimes to find the answers to certain questions. And yeah, this just shows that wall insulation may not be ideal in the summer, and that thermal mass can sometimes work better. So if you look at this graph, the yellow line shows solar, so that's heat into the building. And when we're below this line, that would be passive cooling happening. So this green graph at the bottom here is doing more than the blue one. And that means this wall is just able to absorb more heat. And then it gives it off at night again. So you have this kind of passive flow of energy. And another example of where we have to find a balance would be with natural daylighting. And again, in Design Builder, one can run useful daylight illuminance simulations. And this scenario tested for this residence. So remember, residents would have high glazing ratio to floor ratio. So the thing is, you can actually have too much daylight. And the results here show that, okay, so the lighter, so greener color would be a better result than a blue. And the results showed that with lower visual light transmittance, we get a higher percentage of the daylight in this range that we're seeking, between 200 and 2000 lux. So a great way to find the balance for daylighting. So the data from simulation data can also be superimposed onto surfaces, and this is great for, okay, just double checking. In this case, this roof was designed for locating solar PV panels, and yeah, that's just confirmed in that image. All right, so with that model, the aim was to go to have toward net zero design. So we wanted to balance solar, which is the brown graph here, with the consumption, the dark blue graph, and this is on an annual basis, and it was balanced fairly well, and this work was partly informed by the Getting to Zero guide, where we also showed that our energy use intensity was just under 50, which is the recommended threshold. Also note, we just tested, okay, what would be the effect of electric vehicle and wind turbine, specifically requested by the client. Right, and in the end, here are just some indicative costing numbers, but yeah, it's quite long ago and the prices range quite a lot. Takeaway here would be to, like, if brand names may result in the system costing a bit more, and that wind turbines are not that effective on small scale. We wouldn't recommend that necessarily. Yeah, so yeah, that's basically an overview of getting to net zero design. Marlies, how much time do we have left? Just to quickly check in on that. Do I have 5 minutes?
Okay.
All right. I'll just quickly run you through an example for estimating PV electricity in Cape Town and Johannesburg. So it's a tool that I often use just to double check or test the capacity on projects. So it's PV watts from NREL, National Renewable Energy Laboratory. You type in your address, and if it's near Cape Town or Johannesburg, you will have accurate weather data in this tool. You need to know the system size or have an idea how many panels you can fit on the roof, and then calculate the size. In this scenario, it was on a flat roof, pointed north. And yeah, if you need more information, you just simply click on the information button. But this is basically the information needed to get an estimate for Cape Town or Johannesburg on a residential house, and it fits reasonably well with simulations from solar installers. Right. So for Cape Town, we're generating about almost 6,000 kilowatt hours per year, and if we look at Johannesburg, it's all very close to the same. But yeah, if we look at it at this on one graph, we see that Johannesburg has got a more even distribution across the year, which is a great thing. Probably linked to the fact that it's a summer rainfall, so more clouds in the summer and clear skies in the winter. So yeah, that's much better. You would effectively require a smaller solar system in Johannesburg. So if we're looking at consumption on a typical winter day, so your winter day is the worst case day because there are the least sunlight available, and one would need to design for that. And so here the dotted line is the solar, and in Johannesburg that would be 14 kilowatts. In Cape Town, roughly 10 kilowatt hours for a 4 kilowatt solar system. But this portion would be wasted if there's no plan on what to do with it. So it can be fed in to the grid. Okay, let's look at ways to improve that. The first concept that I just want to mention here is on certain designs, it may be possible to locate certain panels towards east or west. And effectively, you're spreading out this curve a bit so that it's slightly wider, which will increase the number of hours where that sunlight is available. Right. Otherwise, it requires extra battery capacity to store that unused sunlight, or you can also apply for a feed-in tariff. Another important aspect, I think, for net zero or low energy buildings is adapting behavior. And it's probably easier in your own house than anywhere else because you make the rules of how you want to live. So the idea is that this equipment that's being used in the mornings and the evenings, try and shift some of them into the times when the sun is shining, and the performance will be better. So just to recap the main takeaways, building performance modeling seeks to balance between cooling, heating, lighting, and electricity generation. We communicate data graphically or in detail to find and communicate answers. Passive design, as Dolf showed and I mentioned, and adapted occupant behavior contributes greatly to lowering energy demand and consumption. And it's relatively easy to estimate solar production on a residence if you know the roof tilt and the number of panels. Thank you, Marlies. Over to you.
Thanks, Thomas. That was great. I love graphs, so I love these kind of presentations, but I'm also keen to hear from the audience what they thought. And I see there's a lot of questions in the chat, so let's just start with the first one from AJ. Very good question. These climate models are resource intensive, so how do you simplify architectural models to ensure speed and efficiency? Do you create simplified analytic models? Can you extracting analytic models from to be automated? So that's, I think, a lot of questions. Thomas, Dolf, who wants to answer that one?
Yeah, I could. Yeah, so it's multiple questions. So indeed, the model takes time to generate. For example, but we have an efficient process actually where we can take a model and then quickly draw our model over either 3D or a 2D floor plan. And typically we need a simpler model than a BIM model would provide. So a BIM model, for example, you have window framing, all of these details, walls have thicknesses. Actually, our walls just have very thin surfaces, and then all the knowledge is added to it afterwards. To create these models, what is the benefit that we use is actually that we can build onto the SenseXA model, for example. So the SenseXA, where the design modeling, we can reuse that same model, and then so all those other analysis. So what you've seen might have some of the analysis go all out and a bit too far, but typically a PV of the grid analysis or a parametric analysis, then the costs of the model versus the benefits, the benefits are so much bigger than the few hours it extra takes. But does that answer the question?
I think it does, and I think it's also if you have to comply with the Sensen 400 XA and you go the rational route, then the model is already built. So then from there you can do a lot of additional simulations as required per the design. So I think that's also something to with when you design the houses and you can't deem to satisfy requirements in Sensen 400, then the rational route is an option. That would then allow for all these great things Dolf and Thomas are talking about. There's a question about the compost heap. It was the first time I heard about compost heap heating. Very interesting. The question is, would you use the compost heap as a source for a heat pump or directly heat water for radiant heating? How often does it need to be replenished as organic material slows down in activity?
So you could use it directly, depends on what kind of temperatures you need in your system. So if your system uses 35 degrees for heating, which underfloor heating does, then you can use compost heap heating directly, but you can always connect it to a heat pump. So if you use 60 degrees or you want to use it for domestic hot water, you want to boost it up to higher temperatures. So, and the dependent on the size and the material, your compost heap lasts longer or shorter. So for example, we did measurements for Green School in Paal, where we were using horse manure, I think it was at the time, and that the becomes a lot hotter, but it doesn't last as long. And a typical system, if you want to Google it, it's a biomiler. In the Netherlands, they use it. It's a lot of wood chips combined with water, and they make them so big that it can actually last up to a year. But a smaller one can last up to a month or something. So you can design it in such a way that maybe you make sure you have your heating season, let's say 3 months at least, are covered, and then you have to regenerate. And you have to keep in mind that it takes about 7 days for a system to start again. Yeah, that's it.
Great, thanks. Marty, you can unmute yourself.
How's it, guys? Yeah, thanks very much for the talk. I'd rather ask my question because I've tapped like a bit of a mutant. So, and it's not only to Dolf, it's also to Thomas. I'm just interested and kind of blown away with the services that you guys were showing. And I was kind of wondering, both of you, if you wouldn't mind, what is your sort of background that got you into what you are? I mean, you're doing a little bit of mechanical architecture, electrical, environmental. There's like a whole mush in there. So I'm just interested. And then, are you an add-on to a team, or do you actually replace the services of another, professional consultant normally that we would employ? I'm asking from a homeowner or a client's perspective. But yeah, thanks. It was very interesting.
Thanks, Marty. I did put the speaker profiles up on the screens because it went all wrong in the beginning. So I'll skip between the two so you can read those as well. But maybe Dolf, you want to go first?
Want to go first?
Oh. Okay, let me go. Yeah, in brief terms, I studied chemical process engineering and worked in biofuels. And yeah, I was interested in renewable energy and eventually had an opportunity to start working with someone in the industry who was experienced in efficiency of systems in buildings and building modeling, and basically trained with François Hubert. And I've been working as a building performance modeler ever since. Building performance modeling is, I think it's a more well-known discipline in Europe and the United States and other areas of the world. I think it's becoming a more recognized discipline in South Africa now, but it is an additional service. And we are often appointed as part of either, as Dolf also mentioned, Sunstein 400 XA work or Green Star work. But I think building performance modeling for design often has extra challenges involved. So you need to have a bit more experience to do design work as opposed to, I would say, as opposed to certification modeling. That's a brief overview from my side. Dolf, do you want to add?
Yeah, so my background is architecture in the Netherlands, but then specifically focused towards building physics, which then the whole comfort engineering part, but also working experience in a mechanical engineering company and then sustainable consulting companies. That's my background, and also for us, we're an add-on service. So often we're still a mechanical engineer on the team, things like that.
Yeah. Cool. I mean, awesome. Thanks. I mean, is there almost space for a qualification at university that specializes in exactly this, and that we should be teaching kids? I mean, together with Green Star and Well and all these other kind of aspects, the team's getting big.
Good question, Marty. I think there's a lot that we need to add to the curriculum of university studies, including this and including sustainable design and all those things. So yes, I think there's definitely a need. And I think the interesting thing is it's also a crossover, right? So it just touches on the architecture, it also touches on mechanical engineering. So it's a really integral disciplinary profession. But yes, definitely.
Yeah.
Sorry.
I'm sure you would have seen from your involvement in teams on construction projects. Often, that's where the challenge comes. And from our side, trying to manage that that thing where certain consultants traditionally had a role that is now being quite guided by others. And making the whole thing mesh together is often a huge challenge. So again, who do you start with first? I think traditionally it was always the architect, but I think now these days you almost need to start with a lot of these aspects and then let the other guys join if their speciality is needed. So it's turned the thing upside down.
Yeah, I mean, we can have a complete different webinar on like how integrated design should work, right? And who should be first. I think we should all be there in the beginning. So, but yeah, good topic for another time. Sorry, Marty, I'm going to cut you and go to the other questions. There's one from Bala. Given that glazing is the weakest part of the building envelope where most of the heat gain and heat loss happens, true. Where is it not worthwhile to have treated windows, spectrally selective options, as opposed to over-designing shading devices to reduce solar heat gain and cost? Now, this is an interesting question, and I would love to hear from Thomas and Dolf what their answer is, because I think this is one of the biggest things that is happening and coming up continuously in our industry. Thomas, you want to give it a go?
Let me give it a go. Yes, so I think this is exactly why building performance modeling, where it becomes really useful, is to weigh up different options simultaneously. And yes, I think cost is often a really important one. And so spectrally selective glazing may not be cost effective, but as I mentioned in my slide, if there's ways to reduce glazing without it really impacting the design that much, if there are ways to design with smaller windows, that will already make a big difference. And yeah, so I think if you want to move away from external shading, there are other ways to achieve that. But yeah, the data shows us that external shading works the best, and so that's the feedback that we're giving at this point. So if there's really large windows on problematic facades, external shading will work better than certain glazing types that are very expensive in any case. So yeah, so I think there's a balance to be found, and it's also with reducing the size of glazing in problematic areas if that's possible.
Good day, Dolf. Thank you so much for that question. Certainly, you're quite right in saying that obviously reducing the window size would be a better option. However, you'll find that in instances such as the hospitality, that might be a problem because obviously people go there for the views and such. So perhaps maybe spectrally selective windows, or if you cannot afford the glazing, that spectrally selective is another option for window films, which can be applied to non-performing windows or windows that are not performing so well to enhance spectral selectivity, to mitigate the VLT and the heat gain situation. So I just thought maybe it would be interesting to understand your view and your understanding in the subject.
Yeah, cool. Thomas, I could add to that, but you're welcome to jump in as well. Indeed, so as you've seen in my example, there was hospitality, there were large windows, and we definitely went for the glazing. But indeed, we started actually with both the overhang and with spectral glazing, as you call it, and we actually transferred back to fully clear glazing. A well-designed shading element is so much more effective than spectral glazing and window films. It blocks the light versus letting through still most of it, and because of that, the cost-wise, your well-designed shading design will actually always win because you need smaller cooling systems and you use a lot less energy. So it of course differs per climate, whether you're in a Nordic country but let's say in South Africa, typically a well shading design cost-wise always wins from spectral glazing at this point. happy to hear from Thomas and Marloes if they disagree, but it's my
I totally agree, and I'm more challenging the architects to come up with like architecturally pleasing external shading design, because I think there's a lot of, you can design really beautiful buildings with external shading. Thomas?
Thanks for that, Marloes. Actually, I absolutely agree with that as well.
Awesome, all in agreement. There is a question from Jody. My concern about the industry is that every electrician is now a solar expert. Certification modeling does not accept in the real world. My question is, how do we educate the people to be more expertly advise the customers, like myself? And it feels this industry of solar has gotten, rotten. Okay, so I guess in summary, there's a huge demand for solar, but you can be taken, how do you say that? Like, people can take you for a ride when they give you proposals, and I've also experienced that myself. Any comments on that? I think it's actually more a comment than a question, but maybe even the tool that Thomas was showing at the end, you can do your own calculations beforehand so that you know exactly what sizing of solar system you need, and then you go to the different solar systems. Or even maybe our sponsor who's on the call, I think, or he was here a couple minutes ago, could give an answer to that. Dolf, Thomas?
Yeah, I can just add from my own experience. Yeah, we also have a solar system at home, and I think it's very important to get quotations from reputable solar installers. So do your homework and make sure that they are doing good work and have done good work, and also get more than one quotation. And yeah, I think that would at least help with the decision-making process and the overall impression you get from the person who's in charge.
Right.
And just to quick, my side is that, so we experience the same in the Netherlands, for example, with heat pumps, where you get a lot of quotes, but you can't really judge it. And there's a lot of consultants. And the only thing that I can say is that, and I'm sure it's the same for Thomas and Marloes, that we are actually specifically like, well, you might have to say for yourself, but we are independent contractors. So we actually don't push heat pumps, we don't push brands of solar panels. So in our projects, we always double check the specs afterwards. And we do get a lot of, we do catch out wrong installations, wrong heat pumps, wrong PV installations because of that. But it's a tricky thing for a homeowner, because it's hard for them to know how to judge if a consultant, if they're independent and what the quality is.
Right.
Maybe if I can
yes.
just maybe add something from my side. Hi, Johan here. So yes, this industry, as I've witnessed what's happened. We've been in the market now for 2.5 years, and literally in South Africa at the moment, the guy that worked at McDonald's is a PV expert on a Monday. It's caused a huge problem in the market as well. We're busy with certain accreditations. There's going to be a watchdog. I'm part of that journey at the moment, where we will regulate solar installers, and they're going to have to be accredited. PV green card is one option, but I can also say to you that any person can go do the PV green card course and proclaim to be a solar expert. So what my advice would be to say, look, let's rather ask for references, case studies, and has the client or the company been accredited with any of the financial institutions, because that's quite a rigorous progress when they check the balances on their side, in order to make sure that the company credibility is in good standing, in order to be able to arrange finance for those clients. I think that's one of the key factors.
Right. Thank you, Jan. There's one last question, and then I'm going to wrap up because I see we're running out of time. So AJ also asked the question, I see the Durban model, and I think, Dolf, this was based on your presentation. I see the Durban model did not include the floor for analysis, when you do include or exclude, when do you include or exclude floors in your envelope insulation analysis?
I think it was actually Thomas's.
Was
it
it?
might have been mine. Yes.
Okay.
So yeah, I'll attempt to answer that one. So yeah, so we find that that on the ground floor that the floor gives passive cooling if it's uninsulated. So for that reason, the ground floor of a residential building lends itself better to a summer location in a sense. And so I normally wouldn't recommend insulation in the floor unless it's specifically described that these spaces will be used as heated spaces in the winter. And in that case, you can add insulation and it will do less passive cooling, but perform better in the winter when you are heating those spaces. I hope that answers the question.
I think it does. Thank you for that. I'm gonna wrap up. Just want to conclude with this quote, and I think it's very relevant to whatever we've been discussing in this webinar, that the first rule of sustainability is to align with natural forces, or at least try not to defy them. And I think that it's really about getting that passive and low energy design right before we start looking at, throwing technologies at the problem. So some upcoming events. Next month, we're talking about regenerative communities. We've got some very interesting speakers lined up, so definitely want to sign up for that one. Very practical example on regenerative communities. So yeah, that's going to be interesting. In April, we're going to talk happy and healthy buildings. And in May, we haven't decided yet what we're going to do, but it's either going to be waste, timber, or earth ships. So stay tuned for that. If you have an idea, let us know. We're keen. I think Janice has been posting all the links to the different links, so you don't have to copy paste them. And then a very, very big thank you to our sponsor of today's webinar, Solar Solutions and Technologies. Johan, we really appreciate your contribution in making this webinar possible. Much appreciated. And everyone check out their website and get in touch with Johan for a quote, or if you want any PV advice. So thank you very much. And then lastly, thank you to our speakers, Dolf and Thomas. It's been a webinar in the making for a long time, and I really, really enjoyed the presentations. And it's quite amazing. I'm always amazed what you can do with the simulations, and the outputs are as valuable as the inputs. So it's really something, also a lesson taken away. Like, these guys know and understand these systems so well, so you need an expert like them to actually give you valuable information about your building design. So the email addresses are here. Contact them if you want to get a quote, or just have questions for them. Feel free to approach them. And then just lastly, just where our webinars are saved on the GreenNet website. And that's it from my side. I thank you very much for attending, and have a lovely evening, and I'll see you next month. Thank you very much.
Thank you, Marloes. It was great. Thanks.
Thanks, guys.